Okay, so let's continue our discussion last time. So we talk about the Fourier series for periodic signals in the lecture 5. So for any given periodic signal, xt with a fundamental period, capital T naught. So Fourier series tells us that any periodic continuous time signals can be represented into the following Fourier series. So xt can be written as an infinite linear combination of all these Fourier fundamental complex exponential signals. So every complex exponential basis is e to the power of j k omega naught. And the coefficient, the combination coefficient is denoted by ak. So we have k from negative infinity to infinity. So we call this ak the spectrum of xt. And here, for this basis signal, we need to know omega naught. So this is the corresponding angular frequency. So given the fundamental period, this angular frequency is defined as 2 pi over T naught. Okay, so basically, given a periodic signal with this fundamental period, and then this angular frequency is fixed, and then basically the corresponding basis, Fourier basis is fixed. All we need to do is to identify the corresponding spectrum of this signal in this Fourier basis. And we have one formula to calculate this spectrum, AK. Now the formula is given by the following integration. It's given by this integration over one period of the signal. And last time we explained that this can be understood as a kind of dot product between the signal and each of these complex exponential bases. So geometrically, you can understand this as we have a bunch of orthogonal complex exponential bases. So it's EJ, for example, K1. Okay, we have infinitely many of them. And then we want to represent the signal xt under such basis. So what we do is to project the signal xt onto each of these bases. Right, so this is the corresponding projection. Now this length is the corresponding spectrum AK3, for example. And then if you project it onto this one, this is AK1. And similarly, for every basis, you project the signal onto each of them. And this is the projection. So this formula basically gives us a mathematical way to calculate such projection onto each of the basis signals. Right. Now, once we have this projection coefficients AK, we can assemble all these bases with these coefficients into the original signal, right? So this is a decomposition formula. So geometrically, this formula for AK is very actually corresponds to such a very clear and intuitive picture. And in fact, in the previous, so this is a representation of signals in the Fourier domain. And in the previous lectures, we actually talked about another time domain representation. So if you remember that now, if you remember that when we talk about the impulse signals, okay, we have mentioned this equation. So any signal at any time capital T, so at the value xt can be alternatively written in this way. So integration of xt delta t minus capital T dt. So we are looking at a shifted impulse function. Now, actually, this equation can also give us another representation of the signal in the time domain, and this. So here we are considering what is the basis that we are looking at here. Is this all the collection of shifted impulse functions? Okay, so these are the infinite collection of time bases that we are looking at. And then what this equation says is that xt, so under such basis, right, this equation, let's continue. Now this integration is exactly the dot product between xt and each of such time bases. Oh. So basically, this equation is a very intuitive explanation. We have a collection of time bases, time domain bases. So all these impulse functions, right? They lie in the time domain. So and then we are projecting our signal of interest onto each of these basis signals. So xt turns out to be their projection coefficient. So basically, this is to say that under such a time domain impulse basis, the representation of the signal is simply itself. It is just the value of x at a particular time t. And in the previous lectures, we have drawn this picture. So basically, if you have a time domain signal, and we can simply decompose this signal into a linear combination of all these shifted and scaled impulse signals. Okay, and we have all these arrows everywhere. right? So these impulses, this collection of impulse signals, form a time basis in the time domain. And to represent any signal under such basis, the representation is very simple. It's simply the signal itself. Okay, so this is a very straightforward representation of signals in the time domain under the impulse basis. But under the Fourier basis, we have a very different picture. But the underlying idea is the same, except that we are looking at different bases. So this gives another view of signals, right? When we talk about anything, any signal, any object, the first important thing is in what perspective are we looking at these signals? So what are the representation? What is the representation basis? We can view this signal, visualize or view the signal in the time domain, or in the so-called frequency domain, or in any other domain that you can, as long as it is a valid, forms a valid orthogonal basis. And we can see that for a fixed signal, it can have completely different representations under different domains. So last time we talked about this sine signal. So if we look at, so this already gives an example that a fixed signal can have completely different representations in different domains. For example, let's go back to this sine example. Now xt equals to sine omega naught t. So in the time domain, we know that the picture looks like this. So this is exactly the representation of the signal under the time domain basis, right? Under the impulse basis that we just talked about. It's right here. So under the time domain basis, the signal has a very complicated, relatively complicated, complex form. So this is t, this is xt. However, if we represent the signal under the Fourier series, using Fourier series, so last time we showed that okay, you can either utilize the formula for Fourier series, or in this simple example, you can just use the inverse Euler's formula to show that xt, this sine signal, is basically a combination of two complex exponentials. And then these two complex, so this is basically says that, okay, under the Fourier basis, the signal xt can only have two coordinates. One is located at frequency omega naught. One is located at frequency negative omega naught. So this is negative omega naught. And at omega naught, the corresponding amplitude is 1/2j. So this is a complex, this coefficient is a complex number. So it's kind of hard to visualize in the one dimension. So this is AK. Yeah, okay, let me make this formal. So this is actually EJK omega naught. And here should be -1 and 1. Depending on the unit that you are looking at. Here, the unit for the x-axis is this complex exponential signals, e to the power of j k omega naught t. But we are only looking at this index k, discrete index k. So when k equals to -1, the corresponding basis is e to the power of negative j omega naught t. When k equals to 1, it becomes e to the power of j omega naught t. So that those two corresponds to these two basis signals that we are looking at here. Okay, now when k equals to 1, the corresponding spectrum is 1 over 2j. So we are here we have something like 1 over 2j. So that's why we have in MATLAB, when we draw the spectrum, we usually visualize them using a magnitude and a phase of the spectrum. Because in general, the spectrum AK is a complex number, so it's very hard to visualize them in one dimension. So we look at the amplitude. Looking at the amplitude, these two are actually the same. And the amplitude, if you calculate the amplitude, it is basically 1 over 2. Right, because 1 over 2j taking the amplitude is 1 over 2. 1 over 2. So this is the amplitude of the spectrum of the sine signal. And correspondingly, we can look at the phase. So the phase part is the angle of AK. And we can see that these two has a very different phase components. For the 1 over 2j, let's look at this. 1 over 2j, we can convert it into a standard form. So it's basically, I can multiply j on both sides. It's j over -2. So the phase part, so the phase of 1 over 2j, because it only has the imaginary part, right? This is a complex number in the standard Cartesian form. The real part is 0. The real part is, let's look at this. The real part is 0. The imaginary part is -1/2. So the complex vector is at here, which gives us a phase component of -pi over 2. And similarly for the other one, which is the angle, the phase of 1 over -1 over 2j. -1 over 2j equals to multiply j on both sides is -j over, it's actually j over 2. And this complex number is on the positive side of the y-axis, of the imaginary axis. So it's right here. Therefore, it gives us the angle pi over 2, pi over 2. So at location k equals to 1, the corresponding spectrum, right, 1 over 2j, it has a phase -pi over 2. So the phase is negative pi over 2. Let me draw this more rigorously. So this is negative pi over 2. And at the other location, the phase is positive. It's positive pi over 2. Right. So to summarize, for this sine omega t signal, if we represent the signal in under the Fourier basis, then this signal is basically represented using so it has a very simple representation using two pairs of arrows, right? So this is actually a pair of complex numbers. It's a complex numbers. A1 is these two. A1 equals to 1 over 2j, and A negative 1 is negative 1 over 2j. These pair of complex numbers are sufficient to identify this signal in the Fourier basis. And then we can, when we visualize the spectrum, right, we usually plot the amplitude figure and the phase figure of the spectrum separately. So that's what we do in the MATLAB. Therefore, you can see that comparing the representation under the two different bases, we can see that for these sinusoidal signals, it is more convenient to understand them in the Fourier domain than in the time domain. And this is very intuitive because the basis in the Fourier domain, they are basically complex exponential signals, which is basically sine cosine signals in their real and imaginary parts. So if the base signal are sinusoidal signals, then representing the sinusoidal signals under such a basis should be very simple.
I have a quick question.
Yes.
So on that horizontal axis, the 1 and -1, that's when k equals 1 and -1?
Yes, exactly. So this should be k. Yeah. And when k equals to 1, this is understood as associated with this Fourier basis, the corresponding coefficient ak.
Okay.
Is 1 over 2j. Yeah. So this k
Okay.
only indexes the discrete index in this basis. Signal basis.
Okay. Sounds good. Thank you.
Yeah. So this is the so-called spectrum of the signal we talk about Fourier series. Okay, because we know that this collection of bases, they are fixed as long once the fundamental period is given. This one is fixed. The only thing that is changing, that is varying, is the index of the basis. So when we plot this picture, we only in the x-axis horizontal axis, we can only visualize the index. And another intuitive way to understand this is like, you look at k equals to 1, that means at the frequency k times omega naught, the corresponding spectrum of signal is 1 over 2j, for example. So this k gives us so that's why we always call this frequency representations, because we are looking at k omega naught for different k's. So this omega naught is the angular frequency of this periodic signal. So we are expanding this signal at different angular frequencies. Okay, and then for the second example that we talked about last time, again, by using the inverse Euler's formula, this sinusoidal signal can be represented, decomposed into this way. And then by comparing this representation with the standard Fourier series with this one, by comparing them one by one, we can identify different values for a case. For example, here we have a constant value 1. This happens only when k equals to 0, right? Because it does not have any exponential, complex exponential part. So this must correspond to when k equals to 0. And then when k equals to 0, we have a0 times 1. This part is 1. So when k equals to 0, we only have a0. And then by comparing a0 with 1, we know that, okay, a0 must be 1. And then looking at the second term, it has a complex exponential part e j omega naught t. Now this component only occurs when k equals to 1. Therefore, the corresponding coefficient must be a1. Okay, so a1 must be 1/2. Okay. And then you just compare this, comparing every single term one by one. And this term, from the complex exponential part, we know that k must be -1. Therefore, the corresponding coefficient is a -1. So a -1 is 1/2. And similarly for the other terms, although they have a relatively, they have more complicated complex exponential, but then we separate the constant part with the basis part. So this is the basis, because the other complex exponential part, it does not rely on t, right? So that's the key difference. This is a constant base part. Only this part relies on t. So this is a standard Fourier basis, and this one corresponds to k equals to 2. So e to the power j 2 omega naught t. Therefore, the corresponding coefficient, this one, is a2. So a2 equals to this one, and then we can simplify it by multiplying this fraction number, the numerator and the denominator, by j. We end up with this, the equivalent value. And similarly for the last one, you can tell that this is a typo. This should be a -2. A -2 equals to this one. And we only have these 5 terms in this representation. So that means all the other terms, ak, are equal to 0. Okay, there's one question: will the a1 and a -1 always be equal? That's a great question. In this case, you can see that they are equal. And this is because due to the conjugate symmetry property that we talked about last time, which says if the signal is real, in this case, xt is indeed a real value signal. If xt is a real value signal, then we have one property, right? It's right here. If xt is real valued, then ak and a -k, they are equal under such a conjugate operation. But now, since a1 is a real number, so the conjugate is itself. So that means a -1 is the conjugate of 1/2, which is 1/2 itself. Yeah, so in this case, they are indeed equal, because a1 happened to be a real, the spectrum at a1 happened to be a real number. But in general, right? In general, even from this property, we can say that in general, for real value signals, these spectrum, they are not symmetric. if you look, I mean, from this property, you can say that if you look at their amplitude as symmetric frequencies, then their amplitude are the same, because by taking the amplitude on both sides, the conjugate does not modify the amplitude. So if you only look at the amplitude spectrum, for example, for this one, right? This sin t signal is a real value signal. If you only look at their amplitude spectrum, they are indeed symmetric. However, if you look at their phase spectrum, they are opposite. They have opposite phase component. So in general, these two are not equivalent. However, in this special case, the spectrum happened to, the phase part happened to be 0. So these two happen to be the same. Yeah, okay. Okay, so these two examples are very simple examples, right? They are, by nature, they are sinusoidal signals, so we can just utilize inverse Euler's formula to identify their Fourier series representation. We don't have to go through the calculate this AK by following the integration formula. But in general, if we are dealing with general signals, then we have to go over this integration formula. So let's look at this more general example where we have a periodic square wave. So signal xt is given here in the time domain. So between -1 and 1, it has amplitude 1, and then this signal repeats for every 2 seconds. So the period is 4 from -1 to 3, right? So the signal repeats after 4 seconds. So the period is 4. Okay, now given this xt, given this fundamental period, we want to find out its Fourier series. Now this is actually following, you just need to follow very standard steps. So the first step is to identify the angular frequency, which is pretty simple. Omega naught is 2 pi over the fundamental period, T naught. So after calculation, you got omega naught is pi over 2. Okay, and then we compute AK by calculating this integration. So by definition, AK is given by this integration. This is the original definition. Okay. Now let's look at how to specify this integration. So 1 T naught is given, therefore 1 over T naught is 1 over 4. This is specific. And we need to take this integration over any period of the signal. So by looking at this picture, we can take the first period, which only occurs between -1 and 1. So we can only look at integration between -1 and 1. Okay? Take any period of signal. And then within this period, the signal takes a constant value, 1. Therefore, xt becomes 1 in this integration. And then for the rest part, we have this complex exponential part. It's e to the power of -jk omega naught t. So we know that omega naught is given by pi over 2. So just plug it into this exponential. We have e to the power of -jk pi over 2 times t dt. Okay. Now up to this point, this integration is specific. Everything has been specified. And we can see that on the left-hand side, we have AK. Well, this spectrum is indexed by the K, by the discrete index K. And on the right-hand side, we have this complex integration over T. And also we have index K involved in this complex exponential part. So in the end, after you calculate this integration, it should be something depend on K only. And that is the spectrum AK. expression for the spectrum AK. Okay, so next let's calculate this integration. And this is an integration over the complex exponentials. Two commons. Is the period 4 or is 2? That's a good question. Well, when you calculate the period, right, you need to remember the definition of period is that we need to make the signal repeat. So the period actually, if you start from -1, if you start from -1 here, one period actually corresponds to between -1 and 3. So the first half period of signal has an amplitude 1, and the second half of the period, the signal vanishes. Right? So this is one period. We have +1, 0. And then after that, the signal starts to repeat. +1 again, 0 again. So the period is 4, not 2. But if you consider 2 as the period, then signal will not repeat because after +1, you have 0. But it does not repeat after for every 2 seconds. So one period is you can treat -1 to 3 as a fundamental period. Yeah. So yeah, maybe it's a little bit misleading here. So basically, when you take this integration, right, over T0, you should, yeah. So originally you should start from -1 to 3. But then because the signal vanishes between 1 to 3, so basically you can ignore that part. So that's why so there's an intermediate step which I skipped here. So this T0 should be, for example, -1 to 3. And then you argue that because the signal vanishes between 1 to 3, so the integration basically is taking over -1 to 1. Okay, yeah, so be careful when you identify the period. And then this is an integration over exponential function, right? So it's a standard integration. So you just calculate this integration, you end up with this one, and then plug in, evaluate this complex exponential at 1 and -1. So okay, so this is the final result of integration. But in this case, this can be further simplified because we have mentioned this whenever you see a pair of complex exponentials that are conjugate with each other, always record the Euler's formula. So in this case, this one, by the inverse Euler's formula, okay, this one can be reduced to sin pi over 2k. Okay, right, we're looking at e to the power of -j theta minus ej theta. And this is, I think we need to go back to lecture 1 to check that inverse Euler's formula. But this is ej negative theta, so it's cosine theta minus j sine theta minus cosine theta plus j sine theta. So this is the Euler's formula. And then this is basically -2j sine theta. Right, so -j sine theta minus j sine theta, -2j sine theta. Therefore, this one, you simply replace theta by k times 2 pi over 2. So you have -2j sine k pi over 2. And this -2j cancelled with this -2j in the denominator. So you have 1 over pi k sine pi k over 2. So that's the simplest result you can find. So what do we have? We have AK, the Fourier series, the spectrum of this periodic signal, AK for every integer k equals to this one. This is an analytical expression for the spectrum. And this one has a very, if you look into this formula, it has a very relatively simple analytical expression. So when k equals to 0, sine part, okay, wait a minute. When k equals to 0, you have sine 0 over 0. So applied Hopital's rule, you get 1 over 2. Okay. So basically, A0 equals to 1/2. And when k is an even number, when k is an even number, it's 2 times any integer L, you have sine pi times L, which gives you 0. And when k is an odd number, this part takes this value. Okay. So maybe, yeah, let me just briefly comment how to get this result for this for this expression. Basically, so the first case is clear, right? When k equals to 0, you have sine pi times 0 over 2 divided by pi times 0. It's 0 divided by 0. Apply the Hopital's rule, you get this limit 1/2. So this is clear. Now in these two cases, we need to, it seems the value of this sine part depends on the oddness or evenness of this index k. And this is because if you draw this picture, you can see that if k equals to 1, you have sine 2 pi is 1. K equals to 2, you have pi, sine pi is 0. K equals to 3, you have -1. K equals to 4, you have 0 again. So therefore, you can see that whenever k equals to an even number, this angle lies on the horizontal axis, which gives a 0 sine value. But whenever k is an odd number, the angle lies on the vertical axis, which may give 1 and -1. So that's why we have two subcases. When k equals to 2 times L, well, L is any integer. And for any integer L, 2 times L is an even number. So that this is a way to represent even numbers. This 2 times any integer is an even number. When k equals to this one, sine pi k over 2 is sine pi L, which is 0. Because any integer times pi, sine pi L for any integer L is 0. Sine pi 0, sine 2 pi 0, 3 pi 0. And the other case is when k is 2L plus 1. So this is a representation for all the odd numbers. When sine k equals to 2L plus 1, sine pi k over 2 is sine pi 2L plus 1 over 2, right? So continue. Is sine pi L plus pi over 2. Right, sine pi L plus pi over 2. And then the value of this one really depends on, well, for example, if L equals to 1, we are looking at pi pi plus pi over 2. So it's here. So the value is -1. Okay. So if L equals to 1, the value is -1. Now, if L equals to 2, we have sine 2 pi. Sine 2 pi is one entire round, and then plus pi over 2, it goes up. So we end up with this positive one. Okay, continue. You can verify that if it's 3, you have -1 again. If 4, you have 1 again. So it's a kind of periodic structure, and so on. Now this one can be written as -1 to the power of L. Okay. So that's why, right? So to summarize, when k is an odd number, this sign part is -1 to the power of L. So that's why we have this -1 to the power of L in the numerator. And then in the denominator, we have pi k, but now k is 2L plus 1. So we have pi times 2L plus 1. Okay. So a little bit complicated here, but you know, in the homework or in the exam, you just need to get this one, get this result. That is sufficient.
Just a quick question with that. And so on the bottom where it says when k equals 0, it equals 1/2. So would both of the k's equal 0? Because that would give 1 over pi times 0 before the sign.
So in this case, right, we have sine pi over 2 times 0, right? Over pi times 0. So both of the numerator and the denominator are 0.
Oh, okay.
Yeah, so the value should be determined by the Hopital's rule. So you basically take the derivative on both sides and evaluate their values as 0. So that's why you get 1/2.
I see. Okay, thank you.
So following this result, we can visualize the spectrum of this periodic rectangle signal in the Fourier domain. So this final expression gives us a very clear and analytical expression for all the values. And interestingly, they are all real values. Right, the spectrum turns out to be real value only. So we don't need to care about the phase part. So we can visualize the spectrum of this one. So again, this is k. Yeah, this is k, and the y-axis is ak. Now I can visualize the entire spectrum. So k equals to 0, it has 1/2. So it's here 1/2. And then so all the k's, they are discrete. So we are looking at 1, 2, 3, 4, these discrete integers. Okay, so and we have that whenever k is even, this 0. So this is except for k equals to 0. So this is 0. This is 0. And whenever k is odd, we have this one. Now, if you look at this one, the sign changes periodically because the numerator is -1 to the power of L. So this is a sign. This one determines the sign part, but the amplitude keeps diminishing because in the denominator, 2L plus 1, right? As L increases, keeps diminishing. Therefore, for example, when L equals to 0, which means k equal to 1, we have 1. When L equals to 0, we have 1 over pi. So 1 over pi is It's right here, 1 over pi. Now when k equals to 3, which means L equals to 1. If L is 1, we have this -1, and this is 3 times pi. So it's -1 over 3 pi. So this is here, -1 over 3 pi. And similarly for the other side, when k equals to -1, which means L is -1. So it's -1 to the power of -1, which is -1, right? -1. So you have this one is -1 over pi. Yeah, wait, let me think about it. If L is -1, this is -1. This is -1 also. So it's so they okay, so they cancels with each other. So we actually have positive. Okay. And when L equals to, this should be and to get -3, we need to set L to be -2. -2, this is 1, but this is -3, so we end up with -1 over 3 pi. So it is symmetric. Yeah, of course, it's a real value signal, and the spectrums are real numbers, so they have to be symmetric. So this is the spectrum of the signal, the entire spectrum, right? All these red dots, and including this one. So intuitively, you can see that, and we only draw this up to 4. Okay, intuitively you can see that starting from 1, 3. Now, first of all, the amplitude at these magnitudes at these locations are diminishing because the denominator is increasing, and at the same time the sign changes periodically. We have positive, negative, and then at location 5 we have positive again. Right, and then negative again. So that is the spectrum of this signal. So this spectrum shows that for this periodic rectangle signal, most of the components of the signal lies in the low frequency domain, right? Because in this part, the amplitude, the corresponding amplitude is the highest, which means for this specific signal, most of the parts contains low frequency sinusoidal signals. And once we go to the high frequency part, the amplitude keeps diminishing.
I have a question.
Yes.
So this is the frequency representation of this signal, and those are the amplitudes of the frequencies. Is that right?
Yeah. So this is the plot for AK, right? For the spectrum of the signal. So the x-axis is K, the y-axis is the AK. But in general, AK is a complex number. But in this specific example, we know that we can see that AKs, they are all real numbers. So that's why we can visualize them into one figure. Otherwise, we need to draw them into separate figures. One focus on the amplitude, one focus on the phase. But here, the phase is reflected by the sign of these AKs. Right. So this is basically the plot of AK, which is the spectrum of the signal.
So the spectrum of the signal, that doesn't tell us the frequency at a different point, right? Or it doesn't tell us the frequency in general.
It does. For example, if you look at k equals to 4, right? This corresponds to this point corresponds to k equals to 4, right? Which actually means that we are looking at e to the power of j 4 omega naught t. We are looking at these basis signals. So this corresponds to the frequency k times omega naught. And at this point, from this result, we know that the corresponding AK is 0, which means that this particular periodic rectangle signal, it does not contain such a Fourier basis. Right, this is, but or you can know, you can actually, it really depends on how you define the x-axis. If you really want to connect it to the frequency, you can draw another, basically the same axis, is k omega naught, and then so basically you multiply everything by omega naught, and then this will be omega naught 2 times this one. And so on. And the picture will remain the same. And it just tells you that, okay, what are the values of AK at these different frequency locations. Right, and you essentially end up with the picture is the same. Right, because so what we are doing here is, is that once we have this Fourier series representation, right, this part is always fixed, and this basis part only relies on k. So we just need to visualize the AK part. And AK is a function of k, the discrete variable k. So we just need to plot AK versus k. And then when you look at each k, you should connect this with the Fourier series representation. So whenever you have AK here, it is always associated with such a complex exponential basis, which means that, for example, looking at k equals to 1, we have AK equals to 1 over pi. So basically, it means that this rectangle signal, periodic rectangle signal, it contains the part 1 over pi times e to the power of j omega naught t. It contains this signal as part of the component. Right, is this clear?
I think so. I'm trying to kind of, so is this,
Yeah, so look, we are only visualizing AK only here, right? This is AK versus K. Right. So once you have that AK, you calculate the AK following the formula, right? Okay, in this example, you end up with this expression for AK. So you just plot a figure for this AK, and that is the spectrum. That is the spectrum of the for this periodic signal.
okay.
And then, yeah, and then you go back to this Fourier series, and so each AK is already associated with the corresponding complex exponential basis. So you can, so then you understand that, okay, this shows that the signal contains AK times such a complex exponential basis signal.
So we can use this to decompose a signal? But
Yes, exactly.
Probably, okay.
Yeah, this is exactly a visualization of this decomposition formula. We only care about AK part, because the other parts, they are kind of fixed.
Gotcha. Thank you.
Yeah. So whenever we say the spectrum of the signal, we are really talking about these coefficients, complex coefficients that you can. Okay, so this is another example. We are looking at a periodic exponential signal. Well, now between 0 and pi, we have this exponential decreasing signal, and then xt is periodic with pi, period pi. So the picture looks like this. Every period is pi. And we essentially follow in the same procedure. First of all, fundamental period is given as pi, so the fundamental angular frequency is given as 2. Once we have this, we can start to specify this integration for AK. Right? This is the standard formula. Now T0 is pi, so it's 1 over pi. And we are taking integration over one period. So here we consider the first period, 0 to pi, at the first period. Okay, integration 0 to pi. Within this first period, xt equals to e to the power of negative t over 2 is given. So plug it in, this is xt, and the rest of the part are just the complex exponential part. So in particular here, the angular frequency omega naught is equals to 2. So we plug it in, it's e to the power of j negative j k 2t dt. And then this integration is specified. So you just calculate this integration, which I will ignore. I will skip this part. And in the end, you end up with, okay, you first end up with this one. Well, this k is the index in the AK. And then this can be further simplified because okay, let's look at this one. So if you follow the standard integration calculation, right, you will end up with this one, and then you have this. Yeah, you have this one. And you should always be sensitive to the exponents in these complex exponentials. Whenever you see this e to the power of j something times pi, in most cases they correspond to very simple numerical values. So looking at this one, it is e negative pi over 2 times e negative j 2k pi. Right? And because this part, the phase part is negative 2k times pi, which is k times negative 2 pi. It's an integer times negative 2 pi. You can check that this one equals to, okay, let's use the Euler's formula to check this. It's cosine 2k pi minus j sine 2k pi. Now we know sine the period is 2 pi, so k times 2 pi, this is 0, and this is 1. So in the end, the entire part is just 1. Okay. So that's why you have, so this simplifies to e to the power of negative pi over 2 minus 1. And then you cancel the negative sign with the negative sign in the front. In the end, you end up with this one. So basically, you get rid of the k in this exponential part. Now it becomes a very simple numerical constant. So it is this constant divided by 1/2 plus j 2k times pi. Okay, so this is the simplest expression that you can get. And this really helps you to understand the spectrum of AK. Now in this case, you can see that AK is a complex value, the complex number, right? Because of the J, because of the complex unit J here. Therefore, you cannot visualize this spectrum in the 2-dimension. You need to draw the magnitude and phase parts separately. But intuitively, we can see that for the magnitude part, as the k increases, sort of the denominator sort of increases. So the magnitude should be decreasing, okay, as the k increases. So the spectrum is kind of concentrated in the low frequency region. Okay, so this is for the periodic exponential signal. Yeah, and then we can further visualize the how the Fourier series represents or approximates the original signal. So we can approximate the periodic square wave via finite terms in the Fourier series. So basically, going back to this example, now we know that xt, remember, we know that for this signal, right? Once we have this AK, the value of AKs, now the Fourier series tells us that this periodic rectangle signal can be written as a linear combination of all these Fourier basis signals. And then in this, so notice that this is a infinite, it's a summation of infinite terms. So we can try to approximate this signal xt by only consider the summing over finite terms. For example, we can only sum over the first 2 AKs, A1, A2, or the first 4 AKs. So this picture illustrates such approximation by including different number of terms in this summation. So the underlying signal that we are looking at is this rectangle signal. And then if we only include in this summation, right? If we only include A0 and A1, so if we only consider A0 times e to the power of J0 omega naught t plus A1 times e to the power of J omega naught t. Now the summation of these two signals will give us a sinusoidal signal. And now if we increase the number of terms that we include in the summation, we can see that it gives a better and better approximation of the rectangle signal. So each term only consists of sinusoidal signals with a different frequency, angular frequency. And when we further increase the number of terms, we can see the approximation becomes better and better. And in particular, if we go to 16, it is almost looks like a rectangle signal already. And there's a so-called Gibbs phenomenon where you can notice that the approximation is the approximation accuracy is kind of low around the discontinuity point. You can see these small hills, and that is referred to as the Gibbs phenomenon. So these are the points where these are the challenging points for the approximation. Because in general, if you want to approximate such an instant jump by sinusoidal signals, you have to go to infinite frequencies. The frequency has to be infinitely large, and that will cause a lot of Gibbs phenomena around that point. So at this point, we have about a 10% overshoot. So the amplitude highest point is about 10% higher than the square signal itself. And because the spectrum of the signals is concentrated in the low frequency region, so by including the first 16 low frequency components, we already obtain a very good approximation of the signal. Okay. And then next week, once we have this Fourier series representations, we can start to talk about these properties. I have 8 minutes left. Let me see. Yeah, maybe I can go over the first slides. So let's say if we have xt and its corresponding Fourier series. So let us assume that both x and y are periodic continuous time signals. And then let's denote their corresponding Fourier series coefficients as ak and bk. Then, so this is a pair of transformation, right? From the time domain to the frequency domain. So we have a pair of such transformations. And then it satisfies the linearity in the sense that if we consider xt plus yt, consider signal xt plus yt, then the corresponding Fourier series coefficient is simply given by ak plus bk. And this is I think this is very intuitive because these transformations are linear by nature. And then the second property is a very important property throughout the course. Because we will talk about a lot of different types of transformations. Now it says that if xt has a Fourier series ak, then its time-shifted version, xt minus tau, the corresponding Fourier coefficient is given by ak multiplied by such a phase shift. This is a complex exponential with a phase negative omega naught k tau. So basically, the phase of ak is shifted by negative omega naught k tau. So in summary, this is to say that a shift in the time domain, right? xt versus xt minus tau. This is a shift in the time domain. The shift in the time domain will cause a phase shift in the frequency domain. Right? In the time domain, we have a time shift. And then correspondingly, this will cause in the frequency domain, ak, the phase of ak is shifted by negative omega naught k tau. Okay, for lab 3, I think we may need, I'm not sure. I think I have to check the materials. I think we probably need Fourier transform in the lecture 6, but I think the key idea is almost the same. Yeah, so basically a time shift will cause a phase shift in the frequency domain. This is an extremely important property. We will use this to do modulations, and well, we'll see many examples later. So this is really one of the key properties. And then we have this multiplication property. We consider xt times yt. Then the spectrum of these signals given by, this is kind of like this is the discrete convolution between the AK and BK. You can say that. And then these two properties talks about conjugation properties. Now for this one, we have mentioned before, if xt is real valued, then the spectrum is conjugate symmetric. But in general, for any, if x is complex valued, in general, now xt with ak, then we have the conjugate of xt. It has a spectrum a negative k to the conjugate. So it's like considering the conjugation of xt, then the spectrum is reversed and conjugated. You don't have to remember the specific, this properties specifically, but it's good to know where to find them. However, for this linearity time shift, these are the properties that you need to keep in mind, and you need to be sensitive to these properties. And we have time reversal property. If the signal is reversed in time, then the spectrum is also reversed. Okay, so I think here the time shifting is the most important property. And these two are the differentiation and integration properties. Differentiation says that if we look at the derivative of xt as a signal, this as a signal, then the corresponding spectrum is modulated by a constant jk omega naught. It's ak times the value jk omega naught, the complex number. And integration says that if we consider integrating the signal up to time t as a signal, then the corresponding spectrum is given by the original spectrum divided by jk omega naught. So this is division, whereas in the differentiation, we have multiplication. And then you can see that differentiation and integration are relatively complex operations in the time domain. You take derivative, you take integration. However, their impact in the frequency domain are rather simple. It's just multiplication, multiplying by a constant or dividing by this constant. So therefore, this already implies that sometimes analyzing signals in the frequency domain is much more convenient, especially when we have to deal with differentiation or integration in the time domain. Because in general, these operations are mathematically intensive, whereas these in the spectrum domain, they are just multiplications. And we will see that this will motivate us to consider the Fourier transform later. Okay, so I think I will stop here. So these are the key properties of Fourier series. And in the homework, you need to utilize them to solve the problems. So I will stay online in my private Zoom meeting for office hours. So I will see you there.